So let me just start with a reminder on our philosophy. The idea that we started off with a failed attempt to do a scalar theory, a Higgs-like theory, but then we latched on to the equivalence principle. And the equivalence principle told us that we should use not just the mass, but use the total energy and momentum, which then led us to the energy momentum tensor. We want to use this as a source then, and we did gauge theories where if we want a current as a source, we gauge a global symmetry. So you gauge the global symmetry, you get a field theory with a current as a source, and you then note that T mu nu is associated with global space-time transformations, and so our goal is to gauge space-time transformations. So that's what we're going to do today. That's our task today, and we'll get a field theory out of that. And let me just remind you some notation. The Lorentz transformations and rotations can all be absorbed into a transformation lambda mu nu x nu. And the notation I use is the first index is the second index is the one that's contracted. The x lower is lambda mu nu x lower. So again, the second index is the one that's contracted. And so this lambda mu nu is like the type of transformations that we did in Yang-Mills theory, some unitary transformation, which also carries two indices, but we don't often write them. It's a matrix. This is a tensor, two-index guy. This guy would, I'm not really great on the group theory part of this, but be like an SO13 group, and these we did as SUN groups. But basically, they satisfy group properties of multiplication and identities. Here's the inverse mu rho lambda mu sigma is delta rho sigma. So lambda mu nu with the indices reversed is like u minus 1, and this is like u minus 1 equals 1 as a matrix identity. So even though we're keeping the indices explicit, there's no great implicit way here yet. It's basically just types of transformations like we do in SUN. So right before I gauge it, I want to do a little preview. It's the equivalence principle again at work. And here's the idea of local coordinate systems. So let's imagine that we are surveyors and we want to come in and we want to survey and make up a little mapping of our space. And we take our little laser beams and we shine them at the other guy's little cameras, and we try to survey out the space to lay out a coordinate grid. But now we get stuck by the equivalence principle. If I'm sending my laser light out, it actually bends in the gravitational field. And so we're going to start running into difficulties. And so this is surveying with light. So we know we're having trouble there. And the extreme case, here's the picture I always like is, imagine surveying, 3 guys surveying around the sun. Here's the sun. And here's 3 guys surveying by light. They're, A, B, and C. If you would find that the sum of the angles is greater than 180 degrees, and so these guys would become confused pretty quickly. If once you start using light to survey, and if you tried using rulers, the rulers will also sag in the gravitational field. So you're starting to get confused. And clocks, if you have this equivalence between a gravitational field and here's a clock in a gravitational field, and the equivalence of an acceleration, here's my clock in the accelerating field, acceleration, clocks also are going to be confusing. They're going to be moving at different velocities at different times. And so the gravitational field is going to do a job on clocks also. But the equivalence principle comes to work for us. We know we can take a coordinate system that's flat locally. Okay, we just, so even in the gravitational field, if we use some coordinates that were free falling, there's no gravitational interactions, and we can locally do that. Now, of course, you can't do that globally because somebody over on the other side, free falling, would have a different feature. And you can see this here. This light bending is quadratic. So if you make them small, infinitesimal, you can make things flat. So the equivalence principle tells us that we can make locally flat coordinate systems. So let's do that. So let's make little dy alphas. Make our little directions in time and space locally. But that's not going to work everywhere. So we're going to have ways to transform between different frames. So we could use other coordinates. Let's call it dx mu, which is some transformation. Here's the transformation mu alpha dy alpha. So these guys could depend on where we are if we want to transform them. So these guys can now start being coordinate systems that can be patched together and used globally. If we had little invariant distances, squared is eta alpha beta. Y alpha, y beta, dy alpha. In our original coordinates, that ends up being eta. Actually, I needed to do something, an extra step here. We can also invert these. dy alpha is t alpha mu dx mu, we're going to take this to be the inverse. Let's see, I'll write it up here. Sorry, I should have left more room. T mu alpha T mu T, let's see, T mu alpha T beta is up here, mu is down there, is delta alpha beta. Beta alpha. There we go. So then if we're writing these new coordinates, we have eta alpha beta, T alpha mu, T beta nu, dx mu, dx nu. This is going to be the guy we call the metric, g mu nu. And we can use these funny coordinates. We can use any coordinates then. We can use any choice of coordinates here from our flat coordinates if we use the metric. Okay, and then because of the T relation, we'll have a relation in G, which I'll give in just a minute. So anyway, this is just a preview of the choice of fields that we're going to use. We're going to use this metric once we gauge the transformation. Okay, so here let's do it now. So let's gauge is basically gauging Poincare transformations. So here's the general transformation. We have x prime mu is lambda mu nu. We'll now make it a function of x nu, and so Poincare is the Lorentz transformations, including the rotations plus the translations. So if I do it, here's the translation. So plus translations. So there's a general transformation that you can get, a local Lorentz transformation and a local transformation. If you make this infinitesimal dx mu prime is lambda mu nu dx nu plus some little d a mu of x. But at this stage, you can see that the space, if you're making this guy completely general, you can just absorb that into here. You can, if we're being general with infinitesimals, you just absorb it in. And then lambda mu nu of x is written in terms of the little differentials is the coordinates as the derivative of x prime mu dx nu. Okay, so there's going to be our transformation that we're after. We want this to be an invariant. So if we just used eta alpha beta, lambda alpha mu, lambda beta nu, and made these functions of x is not invariant. Okay, sorry, I needed my dx's here. Dx mu, dx nu is not invariant by itself. But from and now these invariants, d tau squared is g mu nu of x, dx mu, dx nu. So that's where we got to from just making general coordinates of using other coordinates. We want this to be equal to g prime. Let's make it alpha beta at x prime, dx prime alpha, dx prime beta. And you can do that if you, so here's the transformation. I'm sorry. So let's see if I can write big enough that you guys can see me here. This becomes an invariant if g prime mu nu of x is transformed just like these other objects that we did. So it'd be lambda mu alpha, lambda nu beta, g alpha beta of x. This would be at x prime. Dartmouth guys, can you see me there? Can you see that? Not very well. Is that any better? All right, let's try that. It's going to be painful. So we can make it invariant if we have that, and for the sake of brevity, I won't write as many equations now, but you can then see that if I have g mu nu, g mu gamma, that, well, so I'm going to define g mu gamma such that we get, that's the inverse, so this is delta gamma nu. So this guy is going to be defined as the inverse. And so the inverse lambda with the indices the other way, this guy transforms with g mu nu upper is the inverse transformation here, lambda mu alpha lambda nu beta g alpha beta, so spaced the same way as before, and we get lambda mu rho lambda mu sigma is delta rho sigma, which then just tells us that the other one, the lambda nu mu, is d x mu d x prime nu. So it's just the inverse coordinate transformation. All right, so I think that's all I've got to say on that. Let's just see if it's solved itself. No. Okay. Okay. If I go back to this locally flat I just want to do a slight notation change here. So we had G mu nu of x is this T mu alpha of x, T nu beta, eta alpha beta. For later things, I'd like to make a notation change at this stage. That's his notation. Sorry, I wrote a little small there. The notation change is I'm going to write now these guys with Roman indices, mu A of x, T mu B, eta AB. And so the flat indices, the ones that contract up to the A, are going to be in the usual Latin. Space-time indices, mu and nu, are going to be mu and nu. And this becomes important later when we do fermions. Fermions are going to carry one index. We're going to need to use these objects with one index being flat and one index being the space-time indices. These guys are called tetrads or Vierbeins. And they transform on their space-time index only. So T A mu prime of x is this lambda lambda mu nu at x prime is T A, so A is unchanged here, nu. Okay. And you can also see that there's a separate invariance on the A indices. It's a Lorentz transformation on the A indices. A mu of x is L A B T B mu of x. So I have now not changed the space-time variables, but there's a separate Lorentz transformation here. Okay. So it's a little formalism. Any questions? Okay, I want to write out an invariant action, and I'm one page away from doing that. The invariant action requires an invariant volume. So if we started off with the volume element being our locally flat coordinates d for y, this is our locally flat. In other coordinates, we would take d for y is d for x, the determinant of partial y with respect to partial x. But in going from one coordinate to the other, dy a is t a mu dx mu. So this guy is just the determinant of t a mu, just the coordinate change that we got from this. And so in our new coordinate system, we'd have that determinant there. And we can also see if I have the determinant of g mu nu, that's the determinant of t a mu t b nu eta a b. That's the determinant of t itself squared times the determinant of eta, which is -1. So if we define, actually, I see I'm writing a little smaller. Are you guys seeing this at all, or is my words being enough? You guys here are okay. Dartmouth? I'm sorry? A little bigger? Okay, let's try for a little bigger. So I'm going to define G with no indices is the determinant of G mu nu. And so then the equation that I have up here, the volume element, dV is d for y is d for x times the square root of minus g. Okay, so this guy is now our volume element for arbitrary coordinates, because I've started from locally flat, gone to arbitrary coordinates. So there's our invariant volume element, and you can show by doing the transformations that this is an invariant, but here's a place where if you want to do a homework exercise, a reasonable homework exercise here is to just do an infinitesimal exercise. You take x prime mu is x mu plus some epsilon mu of x, where this guy is infinitesimal. And then it's a useful exercise to show that this is an invariant volume element. To order epsilon. That exercise is actually a little bit relevant for the weak field limit when we do small gauge transformations in the weak field limit. Okay. So at this stage, we can actually write out our first invariant action. We're looking for S. I'm going to use the scalar field first. The scalar field's the simplest guy. Which is going to be a function of phi, the derivatives of phi, and g. And how can you write out such a one? Well, it's actually not hard for a scalar. It's harder for things, anything but a scalar. But here's our choice. So we start with the invariant volume, d4x square root of g. And we take the derivatives of phi, d mu phi, d nu phi. We can actually leave them unchanged, but instead of contracting them with eta, we'll contract them with g mu nu, which is a function of x. And we get m squared, phi squared. We don't have to change anything there. That's an invariant. Okay? This guy is invariant under phi prime of x prime is phi of x. Here, x prime is some lambda mu nu of x nu. So that's how you transform the coordinates, but the d prime mu, the derivatives transform like vector d mu, lambda mu nu, mu sigma, d sigma. Okay. And g mu nu was, let me not write it since it was on the previous notes. So basically, if you do this, the volume element is invariant. So the second term is invariant. Phi is phi. And if I transform the derivatives this way, and the metric the way I had it on the previous board, then I get an invariant okay. So that's an invariant. Now here, let's see, let me erase this piece so I can do something. We have some immediate success here. We're going to get equations of motion for G. We haven't got its Lagrangian yet, but we do have its source now. If we take delta S delta G mu nu, okay, let me just give you the answer, then I have to erase and do a bunch of little tensor tricks, boring tensor tricks. Okay, but you can sort of see it starting out here. If I take the variation with respect to G mu nu, I'm doing it with the upper indices here. Well, here's the G mu nu, so I get a piece that starts off with a 1/2 d mu phi d nu phi okay, and then the tensor trick that I have to do is tell you how to vary root G, but here's what's going to be the answer is 1 minus 1/2 G mu nu times this whole piece here, which is let's see, the halves pulled out, it's then G alpha beta d alpha phi d beta phi minus m squared phi squared. Okay, this guy looks familiar if you remember the energy momentum tensor. When we did the energy momentum tensor in flat space, we had 1/2. Well, it's the first term except we had an eta there. Let's just say that. And we had no 1/2. So this is 1/2 of what we had of T mu nu. The only difference from what we had before is that I've got G's sitting here instead of etas. But if you take G goes to eta, this is the T mu nu that we had from near this current before. So we've accomplished part of our goal. So we've got a T mu nu as a source, energy momentum as the source. Okay. Questions on that? Okay. Here's the couple of stupid tensor tricks that you need to know to do this. So let's just say that to do this, I use the following. Well, two things that are useful to know. So if we have G mu rho G rho mu rho is delta rho delta rho sigma. There we go. Those are the indices there. That's one of the properties that we did for the metric, and it's inverse. This tells me that if I take variations, I take delta G mu. So I vary this delta G mu sigma times G mu rho plus G mu sigma delta G mu rho. That variation is equal to 0 because the variation of the Kronecker delta is 0. This tells me that if I want to vary upper indices versus varying lower indices, there's a minus sign associated with that, because delta G mu, well, now I'll just rearrange indices. Delta G mu nu with lower indices is then minus G mu rho G nu sigma delta G rho sigma with upper indices. So if you vary upper indices versus lower indices, you need to do that. There's a little minus sign, which combined with the many minus signs of that we can get confused in this course is yet another one. And And the variation of root G is actually a little more tricky. This one is the easy one. So root G is the square root of the determinant. How do you vary the determinant? Okay, so here's how to vary a determinant. We have a variation of the determinant of some matrix. Okay, well, there's this lovely identity. This is in the variation of the determinant of a matrix can be written as the exponential of the trace log. Okay, so you take the exponential of trace log of the matrix, which doesn't seem like a big improvement because now you have to take the variation of log of the matrix, but that's not so bad. This is then e to the trace log m plus delta m minus e to the trace log m. Now here's the utility of this trick. It's e to the trace log m plus log 1 plus m minus 1 delta m. So I've taken m plus delta m as written it as m overall 1 plus m minus 1 delta m. And then the logs are additive. Take minus e to the trace log m. Okay, this guy can be expanded. This first turns into the determinant. I get minus the determinant times the factor that's e to the is then the trace of m minus 1 delta m, having expanded that. So, all right, so there's my general one. That's how you take the general variation. And here, we get the variation of square root of minus g is minus 1 over the square root of minus g. Okay, from varying the square root part times 1/2. Okay, some still from the square root, and then the m minus 1 is g mu nu lower delta g mu nu upper, m minus 1 delta m. All right, so that was what gave you the minus 1/2 g mu nu piece in that variation, and we're fine. Okay, questions about that? So that's just stupid tensor tricks. I will stick to those guys on the conventions page so we have a record of them. So now let's do the matter equations of motion. So we have the matter Lagrangian being this integral d4x square root of minus g 1/2 g mu nu upper d mu phi d nu phi minus m squared phi squared. And the Euler-Lagrange equation for this is then you take the variation of the Lagrangian with respect to the derivative of phi. Well, it's equal to I get the square root of minus g, and I get g mu nu d nu phi. I take the variation with respect to m squared. With respect to phi, I just get a square root of g minus square root of minus g phi m squared. The Euler-Lagrange equation should be then the derivative of the first term. So I'm sorry, what was the question? I'm sorry, what was the question? Is that better? Okay, sorry. I'll write out one of these notebook things afterwards, so we'll get all the formulas down just so we can refer to them. But okay, let's write the equation of motion then. So let me divide by a square root of g just because it'll look nicer. I'm going to take 1 over square root of minus g. Temporarily ignore that. You'll see that that's in the right place in a minute. But I take the derivative of this guy. So I take d mu. No, it's d mu down here because I have an upper there on square root of minus g mu nu d nu acting on phi and then the second piece is just m squared phi. And so now you see I've got the square root of g divided out correctly. I didn't have it to begin with. I'm just dividing both pieces by root g. This then equals 0. This is now our covariant box plus m squared phi. But since we've constructed it using all these nice properties, this is going to be a covariant box, our first covariant guy. And covariant box acting on a scalar. I'm going to write it up here. Box is 1 over square root of g minus g d mu square root of minus g mu nu d nu acting on a scalar. Okay, it won't be that guy when acting on a vector, because we're going to have to construct that next. But this, when acting on a scalar field that transforms the way our scalar field transforms, this is our box operator. Okay, yes? So yes, so we had, so now what's really invariant is the action. And so I've got the square root of g in the d4x. If I then just go back and repeat my usual Euler-Lagrange derivation of varying phi, you'll see when you do the integration by parts, that's part of that derivation, that it has to act on that root g also. Okay, so I have got the root g's in the right places. That root g has to be there to maintain the invariance. Okay, because what you really make invariant is the action, and the root g is part of the action. Okay, the question was about whether root g in the Lagrangian was part of the Euler-Lagrange equations, but if you just redo the derivation, it is. Hi.
Some authors just, they separate, so they still take the covariant stuff, square root of minus g, the Lagrange.
Well, yeah. This is the right equation of motion. Yeah. Okay. And if you go back and you do the principle of least action, you will get this out as the. So this is, at the moment doesn't tell us that this is gravity. When I do the linear case in a couple days, we'll look at this and we'll find in that the Schrodinger equation in a gravitational field, so that it will be gravity, but we're a couple steps away from that being gravity yet. Right now it's just an invariant equation of motion. All right, now comes, hi, come on in. No. So now comes the fun. Remember, so here's the quickie preview. We still have to construct we want some equation that's roughly, something like box G is something like T mu nu. Okay, we've got that side now by varying G, so we need to do something. We need a Lagrangian, we need an action for gravity, which is something that involves G, which when you vary it gives you something that looks like that. So we're something like that. So you could try, something like d mu g alpha beta, d mu g alpha beta, things like that. But this doesn't work. This is not invariant. That's not invariant because it's badly constructed. The derivatives here on the coordinate changes wouldn't cancel out. But that's just like what we would have said even in E and M. You can't do d mu a nu d mu a nu. That doesn't work either. Okay, so you can't just blindly put this in here. You have to construct it. You could start guessing. You could just take all different combinations of this and painfully start guessing it, and I guess it could work. But the construction that we did to get this is we did the d mu commuted with d nu on some psi, and this turned into F mu nu on psi. And so we're going to try to do this sort of the same thing here. G mu d nu is going to go to some stuff which is curvatures, or mu nu dot dot dot. That's the goal. Okay? So rather than just start guessing, let's construct it. Okay. So the pathway is to do a covariant derivative, and I'm going to reserve fermions for later. Fermions are a more interesting and more elegant and more beautiful case, but extra work. So let's do it instead on a vector. So we have some vector field, V mu. It's going to go to some V prime mu, which is this lambda mu nu of x, V nu of x. So here's its x prime. So that's our vector transformation that looks just like the vector. So if you did this and you had a V mu upper and a V mu lower, you could make this into an invariant just by contracting indices. But derivatives wouldn't work. So what you would like to make it work is you would like a covariant derivative. So you want this. You want something. So if I have a covariant derivative mu V lambda of x, you want that to go to some change derivative V prime lambda of x, which is, well, x prime, that these guys just transform like everything else does with these lambdas. So the lambda mu rho lambda lambda gamma d rho v gamma. You guys see the corner out there okay? Okay, good. So basically, you want this thing to transform normally like any old tensor. Okay? The general form is the following: is d mu v lambda is some d mu, the partial usual derivative, and then there'll be this new piece which is like the gauge field mu nu lambda, and in my convention I'm going to keep those first two spaces empty, and lambda sits off to that side, and V nu. Okay? Now if you were fortunate enough that these things was a delta lambda nu, then you'd have a very simple theory, but in general, this isn't going to be the case. There's the general transformation. And so, since this guy by itself isn't going to transform properly, this guy has to transform in such a way that it cancels off this transformation here. All right. And I've got a half a page of algebra, which I wasn't going to do all of it anyhow, but let me do none of it then. and just give you the answer, okay? Because it's going to be too long, and the time's not right anyhow. So V transforms this way. Gamma prime lambda mu nu of x. Okay, it's going to have some piece that transforms like a general, like you expect it to do. So let's do lambda mu rho lambda nu sigma lambda lambda eta. Okay, so these are just the transformations that would look like if it just transformed like any tensor does. So here's the gamma, and it's now rho sigma eta. Okay. But if it did that, it wouldn't cancel off the extra piece. To cancel off the extra piece, you need now a new term, which is lambda eta alpha d rho lambda alpha sigma. Okay, so the half page of algebra was designed. Okay, I didn't even write out the condition though. So let's write one more line as the condition. So I wanted d prime mu v prime lambda of x prime to be equal to just the usual transformations. No, I did. No, I wrote it out there. Never mind. Sorry. It's this guy. I wrote it here. Okay. So going from this want to this step is just basically you plug in v prime into here, you plug in gamma plus into here. You can just verify that if you want. Okay, lots of stuff. Okay, I'll actually derive this soon. Oh, no, actually, I haven't given you the answer yet. I'll derive it. At this stage, I'm just going to give you the answer. In fact, that's probably a good place for me to stop today. So how can this work? Okay, the derivation comes next time. That's good. Keep you in suspense. The derivation is actually simple once you do one little extra piece of work. So this is solved by okay, so gamma mu nu lambda sitting out there is 1/2 g lambda sigma usual derivative acting on g nu sigma plus usual derivative nu acting on g mu sigma. So symmetric in mu and nu, g mu nu, usual derivative sigma, sorry, backwards. Derivative sigma g mu nu. Okay, this is actually not unique. We will come back on that, but the phrase whenever I want to say not unique, I will use the phrase torsion because the non-uniqueness goes into the concept of torsion. But you can verify that it works, and I won't start it, but you basically just transform G the way I told you to transform G. You take the derivatives, you add up this combination, you get that result up there. The non-uniqueness part of it, it is unique if gamma mu nu lambda is taken to be symmetric in the mu nu indices. Gamma nu mu lambda. So if it's symmetric in the lower indices, then it's unique. Okay, and it is symmetric in the lower indices. And you'll see that actually in the derivation that I do next time. Okay, let's break there. So next time I do a little bit more on tensors, and I construct using this the curvature. Okay, very good. Good. Yes. Okay, sure. So sorry, guys. I'll write out something and try to post it anyhow. Okay. Okay. The pen stopped writing on the tablet.